Hi, this is 3D Printing News Unpeeled, live with yours Peels. And I'm the executive editor of 3dprint.com, and I'm vice president of consulting at Smart Tech Analysis. And I'm going to bring you hopefully a timely, hopefully a useful for you news roundup of the top news stories in 3D printing for today. So on number 6, we have a story from the Royal Netherlands Navy and Nanoe that they're going to partner to to print spare parts for the Royal Netherlands Navy. So Nanoe is a French company that makes filament, so bound filament with ceramics or metal components in it. It makes printers and it makes sintering debinding equipment, and it gives you all the recipes you need to print bound metal components. I'm a huge Nanoe fan, by the way, and I think this is a very good idea for the Navy. So Nanoe, I think, is a good partner, has very deep knowledge in this. And what other alternatives do you have, really? So powder bed fusion on board a ship is a very bad idea because the powder can explode and catch fire. And the machines are actually also quite large. You could maybe do WAM or DED on board a ship. That could be interesting. Wire DED definitely could be very interesting. Um, you know, Binder jetting would be good, but those machines are typically quite large as well. So with Nanoe, you can run the filament on like an Ultimaker or another kind of desktop type 3D printer. So that makes the overall package. If you look at in the middle of the guy standing there, that's a sintering machine as well. So the overall package of the components you need is also quite small as well. Now, of course, debinding and sintering is not without kind of risk. There's some things you need to be careful with. But all in all, it's a really compact system. It's a cost-effective system, as in the implementation cost of one system is very low, much cheaper than a binder jetting system, much cheaper than, for example, getting another kind of bound metal type system, like a Markforged, for example. And also you could develop workflows for very simple materials. Now, of course, the Navy is very interested in metals and metal replacement parts. The bound metal typically means you don't get as detailed as fine parts as you would with binder jetting, but you can make bigger parts, kind of rougher parts. And you can make quite large parts with it as well. And the other thing is, not only is the machine cost effective, so machine, the sintering, all these components, but the part cost is also very low. So I think more navies should really explore these bound metal systems as an onboard supply solution for them. So I think it's a very fruitful area, and I think it's great that these guys are working on this. The next thing is the wrap, the wrap machine. The wrap is a machine that can cure, well, essentially the first version of this machine, what it did is it cured leftover photopolymer. So the photopolymer materials are quite dangerous and for human health, and also for things like contact allergies if you touch them. Disposing of them is actually quite complicated and quite annoying in an office setting, as you may have found if you do this yourself. And also, depending on the country, it might be quite difficult. You have to get them to a special chemical box type recycling kind of facility or something like that, depending on who you are and where you live. So what these guys do is they kind of wrap the resin essentially, and they make a big roll out of it that you could theoretically recycle, but well, don't count on it. But what is true about that is that because well, you can theoretically recycle, I say, but not in a meaningful way. But anyway, so what you can do then is dispose of this stuff much easier. So you have these last bits of resin in your bottle, maybe bits of resin left over, resin that's stuck in the build platform, that kind of thing for material change. You can take it all and it turns it into like a big giant roll kind of thing. So that's I think for a lot of service environments and also research environments, that could be a very interesting proposition because you could dispose of this much simpler, and it's also safer in the handling for your staff. But now they've turned the machine into like a post-curing machine as well. And you just switch over from the resin wrapping mode, if you will, to the post-curing. And what they have in the post-curing is they cure from all sides on circular kind of rotating build platform that's transparent. And the idea is that they flash an object from all sides. Now, theoretically, this could mean it flashes faster, It also means there's less handling, because in some other systems, or most other systems, you have to reposition the part because it doesn't flash from the bottom, or it does so, but through a grate or something like that, and incomplete. It's incomplete. So this should be kind of a potentially much more repeatable, and also maybe even more reliable way of flashing parts. So, and this could work for DLP, SLA, or other kind of parts that need to be flashed. So I think this kind of innovation is to be applauded. I think this could be a very exciting way to, in a quickly, reliable way, flash objects with a UV cure. The next thing, this is development that, well, essentially a Caracol machine has been used to print furniture. This furniture was developed for a specific Italian tower, in Porto Venera, the Torre Capitolare, which is built in 1161. The polymer used is recycled polypropylene, which is GF loaded, and also has seashells in it. Actually, a friend of mine, Carmen Brio, was the first person to print with seashells a really long time ago, the FDM. So it's nice to see people continue on with that work. But the idea that really inspires me with this, like Dirk van der Kooi in 2014, if I'm not mistaken, first demonstrated 3D printing furniture. And a lot of people have copied him since then with similar methods, with using robot arms and stuff like that. But what I like about this is that this particular design project kind of customized this furniture for this location. They also added in seashells. We don't know what percentage of seashells. And that's, of course, a nice kind of touch, given this is like a tower, and a lot of this kind of similar materials are being used. And what this got me thinking, like, if we're looking at, like, from a 3D printed furniture making kind of viewpoint, it's nice to have 3D printed furniture. What you could do as a designer, you could make one base design or one kind of family designs, and quickly customize it through different patterns and different tweaks in that design to a given location, to match their architecture more, or to match their local requirements, or to match a certain pattern found in the building. So, in that sense, it really got me thinking that this could be a very a very kind of exciting way to, as a designer, say, look, this is the basic collection, but we're going to give you your castle, your hotel, whatever, completely unique furniture that no one else in the world has. And that kind of customization could also be very easy for you to do. So I think that to me was, there's a good kind of an idea to have. It was a really obvious idea, of course, but I don't think a lot of people have really implemented it correctly. The next thing is the research of Fergal Coulter. And Fergal is a researcher that's currently at ETH Zurich. And he does things like silicone heart valves and stuff like this. And I just stumbled upon his research today, and I think it's really inspiring. And I think one of the things is inspiring as a researcher. He's got a really clear website that showcases his research and showcases what he's doing. He's got a YouTube channel that shows all the videos of what he's doing. So he's really going the extra mile to make his research very accessible, not locked behind some kind of paper somewhere or locked behind some paywall. It's really out there and it's accessible. And I think that as a researcher makes it much easier to fall through the rabbit hole of somebody's research. And it makes it also, much more accessible to lots of people who maybe don't work at institutions. So I wanted to applaud that, first of all. And the other thing is that you see a lot of plodding research in 3D printing. We need it, right? But this is some really, really very, very creative stuff. And the thing that really caught my attention initially was this 3D printing on top of balloons with elastomers, right? And these elastomers, of course, can then be printed kind of conformally to the balloon. And the balloon kind of acts as a support material. And the elastomer itself can be inflated and deflated afterwards. Now, you can obviously see that this, for implanting things in the body and stuff, is a really very exciting kind of path forward to making these things more compact so they go in the body. But also just using, and this picture shows it a little bit more clearly. So if you see the first picture is like this, and then if you see the next picture, this is a kind of a more closer to finished structure. You can see that if that printing such a structure loose or freeform would take a lot more time. You'd need a lot of support material, or you wouldn't be able to do it. And then using these balloons as support, essentially, opens up a lot of possibilities, and opens up a lot of possibilities in making these things very, very quickly. And also the idea of making inflatable elastomeric structures, I think, is something that in the shoe business or in making sports equipment or anything like that is something that really, really has a huge, huge potential. And a lot more people should be looking at this. So I really found this super inspiring, this work. So, and I hope you do too. I have the links. I'll put the links to the work below. Next, we have a team that is looking at, well, they're at the Materials and Technologies Group at the University of Basque Country, and they're looking at personalized starch tablets. And what I liked about this is not only like personalized printing of personalized medicine, which of course is better because then, a different disease stage or a different readout or a different kind of test score or something like that, or a different weight, a different type of patient, and you can get a different personalized tablet, right? Now, using starch, which is like super cheap and really available and very, very safe because we consume it often, also has an added advantage for hydrophobic medicines and printing hydrophobic medicines. But on top of that, the one thing I hadn't sufficiently considered was the fact, of course, that with these starches, you get different release kinetics. So with the release kinetics can be changed through the geometry of the tablet, through creating things like gaplets or kind of breaks and things. But what the researchers here have found, of course, that these non-soluble drug loaded tablets, which they printed using potato starch and two types of maize starch, have different release kinetics. Now, this is, of course, obvious. We know this from cooking, for example, and all this. But they like the fact that the drug release is instantaneous in the normal maize starch, right? The drug fully releasing in 10 minutes. Now, if we then use exactly the same geometry, and then use a waxy maize starch or a potato starch, the release is continuous for like 6 hours. All right, so imagine just looking at a medicine and saying, just changing all these different starch, giving different recipes of different starches to really change the release kinetics. So that's another thing you could be doing on top of just changing the geometry. And that idea in and of itself, I thought was something that is well worth some people looking at, because to me, that could have a lot of answers to this personalized medicine. I really think that this kind of stuff, it seems far off for a lot of people, but it's not that difficult compared to some of the other stuff we're doing. But the impact is huge. Thinking about, like, for example, a polypill kind of setup where we're talking about a geriatric patient who may have to take like 6, 7 different medications at 3, 4 different times a day, and then also have dementia at the same time and be in an elder care home. So it's either going to be a very big burden on an elder care home, or it's going to be almost impossible for that person or that person with aid of relatives to keep their required medicines. Now, this elder care home example is not an idle example. We're going to have the largest group ever in elder care homes in a decade or two, and and at the same time, we're going to be facing worker shortages. So things like that is a real example where in an elder care home or an assisted living facility or something like that, you would really want to be able to print exactly all the medication or almost all the medication that person uses in one pill or two pills, right? To be released during different types of the day or during the day and that kind of thing. So these applications for me are very exciting. And then also just the idea of, like, we both take an aspirin. I might weigh twice as much as you or something like that, or I might function completely differently. But we're both getting the same aspirin. Of course, there is a lot of potential there to get better aspirin essentially, or better dosage of things, and better medicine. So to me, this is a very fruitful area here. Now, the next thing is the number one news item of the day is a research paper, and you're like, oh, really? This is boring. Now, this is definitely not boring. This is, first off, it's an open access paper. And thanks to the US government now, we're going to be probably seeing a lot more open access papers by government funded research. So this is very good, because it makes it much more accessible to also people in industry, but also people in developing countries can really have much better, easier access to this research. So that's good. Its paper is called Robust Metal Additive Manufacturing Process Selection and Development for Aerospace Components. It's by Paul Gradle, who's of NASA's Marshall Space Flight Center, and a bunch of other people also working there and other parts of NASA. And it quite simply is it's one of the best papers I've ever read on additive manufacturing in terms of, like, it's being useful. It's a completely useful paper. It's very clear. What it talks about is DED and WAM. And process selection, like, what do you do, right? What are the parts of trying to select a process? How do you select a different material or different kind of process to match a particular component? How do you qualify this component? How do you make this? What are all the different variables and things you have to take care of and all this? And I literally think this is an astoundingly good paper. It's really, really helpful. And definitely if you're into metal additive manufacturing, even if you're a beginner, this is going to be a fantastic paper for you to learn about all the important variables, let's say, and the process of kind of trying to go from nothing to getting a really, really tough to make part that you want to make according to specifications. You're going to learn a lot from this. But even if you're like an old hand, you think you know everything about metal additive manufacturing and all this kind of stuff, this is a really great guide and really great stuff. And I learned a ton from this, and it's a really great paper. So I really urge everyone to read this. And I'll include the link to this in a bit. And yeah, thank you so much for listening today. And thank you so much for your patience. And this is another edition of 3D Printing News Unpeeled. And my name is Joris Peels of 3dprint.com. Have a great day.